Gradient descent is at the heart of supervised machine learning. It could be statistical machine learning or a deep learning. And in this video, we are going to cover exactly this topic. So we'll go through some theory first and then we'll write Python code to implement gradient descent. Now, if you have seen my machine learning tutorial series previously, I had a separate gradient descent tutorial that was specifically built for a regression problem for housing price prediction. In this video, we are going to cover some of the same theory, but we will build gradient descent for a simple neural network or a logistic regression for an insurance dataset. So if you have not seen my previous video, I would highly recommend you see that. And if you don't have time, don't worry. I will try to cover most of that theory in this video as well. Now, if you're targeting a data scientist role or a machine learning engineer role, gradient descent is a common topic that they ask in the interviews. So it's very important that you understand the math behind it, you understand how the technique works, because it is, as I mentioned earlier, at the heart of machine learning, especially supervised machine learning. So gradient descent is everywhere. It is the core of ML domain. So that's what we'll cover today. Let's get started. Let's start with a little quiz here. I have x and y values and I want you to figure out the relationship between the two. So the function that describes the relationship between these two variables will be y is equal to x into 2. Alright, how about this? Pause this video and figure it out. What is the linear equation for this table? Well, this one is also easy. Y is equal to x by x into 3. How about this? Okay, again pause this video and try to figure it out. Well, this is x into 2 plus 3, because let's take an example. If x is 2, 2 into 2 is 4, plus 3 is 7, so you get 7. X is 3, 3 into 2 is 6, plus 3 is 9, so you get 9. Alright, how about this one? Well, this might not be that easy, correct? The smile or the curiosity this little child has is actually valid, because as a human being sometimes you have hard time figuring out relationship between these two tables. But if you give this to a computer has a technique called a gradient descent. Using that technique, it can find out the linear equation for this table. And this gradient descent is at the core of machine learning and deep learning, especially supervised learning, because in supervised learning you have truth data, which is x and y. So you will often have this type of table. And then gradient descent, all it does is it finds the relationship between these two. This is also called a prediction function, so that tomorrow if you have a new value for x, let's say 11, you can put that into this equation and find out the value of y. Here 0.5 is called weight and 1.5 is called bias. This is simple linear algebra. As I mentioned before, this is a prediction function and it's the main point behind any supervised machine learning technique. Could be regular machine learning or a deep learning. Let's look at our insurance data set now. Let's say you have a table, age and affordability, and have insurance, which is output column. Now we have talked about this insurance data set in our previous tutorial as well. So if you have not seen my previous video, I would highly recommend that you watch those. Here, based on age and affordability, we can say if the person is likely to buy the insurance or not. And often in binary classification type of problem, which is this type of a problem, you want to find a function that can take age and affordability as an input, and it can tell you whether person will buy the insurance or not. So age and affordability is obviously x, y is having insurance, and all you're trying to do is simple, trying to figure out this function f of x. And we have seen in our previous videos that we can define a simple neural network with a single neuron. We have two neurons in the input, but often when we are talking about neural network, we don't take into consideration the input neurons. Hence this has only single neuron, and it's a logistic function. We have already seen in previous tutorials that logistic regression can be thought of as a very simple case of a neural network having a single neuron. And in logistic regression, you all know there are two components. One is the weighted sum and the second one is the sigmoid function. Alright, now when you're training a neural network, and remember that gradient descent is used during the training of a neural network. So let's say I have this 13 data samples. So I have this truth data which has 13 data points. I want to use all of this to train my network. So what I'll do is I will first feed the first sample. So age is 22. So 22 is here. Affordability is 1. 1 is here. And I will initialize the weights to some random value. Here I initialize them to be 1. So you see two purple ones here, 1 and 2. And I will also initialize bias, which is here in purple 0. So I initialize them to 1 or 0. You can initialize to some random value as well, doesn't matter. And then you feed the first sample into this network. This is called a forward pass. In the forward pass, you will put the value of age as 22, affordability as 1, and then you get a value of y. Then you put y here and get a value of z. For this sample, it will be 0.99. And your truth data is 0. So what you predicted was 0.99, and your prediction value is often indicated with y hat. So whenever you see this hat or a cap on top of y, it is a predicted value. You have predicted value and you have the truth value. So you find out the error. So the error we have seen in a previous video that for logistic regression, we use log loss. We don't use mean square error or a mean absolute error. And there are reasons behind it. But we use this log loss, and this is a mathematical equation for log loss. Don't worry too much about this math. You can just think of it as some kind of error function for a log loss. And you find that your first error comes to be 4.6. You will repeat the same process for your second sample, which is 25 as age, 0 as your affordability. Again, you find out y hat and y and calculate the second error. Here y hat seems to be same as the first sample, which is 0.99, but that's okay. You go through all the samples until the last sample, which is the 13th sample, where the age is 27, affordability is 0. You feed that, you get y hat to be 0.99, your actual y is 1, and your error number 13 is 0.01. So now you sum up all the errors for all the samples, and then you calculate the loss. So here we are using log loss, which is also known as, by the way, binary cross entropy. And that is nothing but sum of all the losses and you take the simple average of it. So after the first epoch, so what is epoch? Epoch is going through all your training samples once. So once you have gone through training sample number 1 to 13, that means you have completed one epoch. After first epoch, your total loss is 4.31. And I'm just making this up, but you can do the math. And then your goal is to back propagate this loss so that you can adjust this weight 1 and weight 2. Remember that when you train neural network, you might have to run multiple epoch until you get a correct value of W1 and W2. So after the first epoch, my log loss was 4.31. I need to do something to now update the weights W1 and W2 in such a way that my log loss can be reduced. So my goal is to adjust W1 and W2 such a way that the log loss is less than 4.31. So how do I do that? Well, from W1, I need to subtract some value. I need to adjust it basically. So either subtract or add some value. So what is that value? Now, if you've seen my derivative video in this same series, that's why I keep on repeating that you need to watch previous videos so that you have that mathematical background, so that whatever I am talking about doesn't make like, you know, it doesn't sound like a rocket science, because it is not. So derivative. So now let's talk about derivative. So derivative of your loss compared to W1 indicates the what it will indicate is how my log loss changes for a given change in W1. And that's an important parameter to understand, because now you can do something like this. You can say that something is actually learning rate into, this is a derivative of loss compared to or with respect to W1. Learning rate is usually 0.01, that's the value people use, but it's a small value so that you don't adjust your weights too drastically. So learning rate is just limiting your derivative function. And what this is saying is how the loss is changing for a given change in W1. And for W2, the equation is same as W1. And for bias, again the same thing. It's just that you are taking a derivative of loss with respect to bias B. Okay, now for our log loss function, the derivative seems to be this equation on the right hand side. Again, do not worry too much about math. Don't think I am not good in math. I used to get 5 out of 100 in my math class. That's why I suck at math. You don't. Math is not as hard as you think it is. This derivative function is something that we got using the derivation formula. And again, in our derivative video, we looked at various ways of calculating derivative function. Mathisfun.com is a great website if you want to refer to math in detail. But for here, just assume that this is the derivative. Okay. And again, for the bias, this is the derivative. I have not shown the derivative for W2, but it's same as W1. So now we started with weight 1 and weight to be 1. Our bias was 0. We found a total loss which was 4.31 something, and then we used this derivative to find the new value of weight 1 and weight 2 and bias B. And then we find that the new values will be this. So now my new weight is 0.8, W2 is 0.7, and my bias is minus 0.2. Now you repeat. Once you got this new weight, you again feed your entire training set to your neural network, and you do a forward pass. So you first feed the first sample, you find out the y hat and y, then you calculate error number 1, then you feed the second sample, third sample, until the 13th sample, and then you find the total error. So this is the end of second epoch. And by the way, we are using a batch gradient. If you are using stochastic or a mini batch gradient, the technique will be little different, and we will go into the difference of these 3 gradient descent techniques in the later videos, so don't worry about it. Right now we are using batch gradient descent, where you need to feed entire training data set for one epoch and before we start backpropagating. So this is the second epoch, and if you remember from our handwritten digits classification neural network, epoch was one of the parameter when you called model.fit in your TensorFlow code. So we have looked at this before, and now you can kind of make sense of what this epoch is. Okay, so now when should you stop? So let's say you run second epoch, third epoch, fourth epoch. When would you stop? So usually, if your error function is a convex function is nothing but like a boat like a function like this, where here this chart, again friends, it's a very simple chart. On y-axis you have loss, on x-axis you have W1, and it's a 3D chart, so x-axis has again W1 and B. I have not shown W2 because you cannot visualize four-dimensional four-dimensional data easily in our 2D screen. So this is the best we can do, but it mathematics wise it works equally. Doesn't matter it's a 2-dimension or 10-dimension. So if your loss function is like a boat, this looks like a boat, the boat in the river, so you start with some random weight and random b, and your loss is usually high. So let's say you start at this point, and when you use derivative, you are constantly shifting or moving towards a point where your loss is minimal. So here at this bottom point, your loss value on a y-axis is minimum. All you're trying to do is find out the value of corresponding W1, which is, see here, maybe 72 or something, and the value of B, which is here near to -5. So you're trying to find these values. Once you find these values, you're done. You have your prediction function. And gradient descent allows you to do exactly same. You are traveling from some random point to a global minima. This rate point is called global minima. Now if I take an intersection and if I visualize this in a 2D plot, this is a chart of W1 versus cost. This is the B versus cost. And both the planes are like this. They're like both type of U-shaped function. And you start at a random point where the loss is very high, which is the star. And you're trying to gradually move to a point where loss is minimal. And that point is nothing but a global minima. So this is your process. And in this process, at every point, you are drawing a tangent. And that tangent is nothing but a derivative. We have seen in previous videos. So that's the derivative. And then using that derivative, you multiply that with learning rate, and you try to move from this point to this point to this point to gradually here. Alright, enough of the theory. Show me some code. Let's write some code so you get even more better understanding of what's going on here. So I have a Jupyter notebook open here where I have imported my insurance dataset, and if you look at the CSV file, it looks something like this. Age, affordability, and whether person bought the insurance or not. If you don't want to use Jupyter notebook locally on your computer, you can also use Google Colab. That's perfectly fine. Now I have loaded my data into my data frame. Until now the code should be familiar, pretty straightforward. Now I want to scale my data. I want to do pre-processing because my affordability is in a scale of 1 and 0, whereas my age could be from the scale of, ideally in theory, 0 to 100, right? Or less 1 to 100. So I will what I will do is, first I will do train and test split, and you have seen my machine learning tutorials. It's very easy. So this is how you do train and test split. You import a train test split, and then you call this function on your data frame. My test size is 20% of the samples, okay? And if you look at my X train, look something like this, okay? And the length, if you look at it, is 22. Whereas if you look at total number of samples, 28, okay? So 22 for training and 6 for test. All right, now let's do the scaling. So for scaling, you know that if you want to scale your age into 0 to 1, and since the age is from 1 to 100, you can just divide it by 100, and you can do something like this. So here I made a copy of my data frame. I'm calling it X train scale, and then I'm dividing age by 100. Okay, same thing I'm doing with the X test. So when you do that, my X train scale, you see my age was 22, I converted to 0.22. So now this number is between 0 and 1. And why do we do this? Well, because to bring the age and affordability on a same scale. So if you do scaling, your machine learning model tends to work better. Okay, now what we'll do is we will use first TensorFlow, and we'll build a simple neural network for predicting the insurance. Okay, so if you know from my previous tutorial, the way you create Keras model is by doing this. So here I'm creating a sequential model with only one layer, where my neuron is just 1 and my input shape is 2, because age and affordability, there are 2 parameters in the input, and my output is 1, which is telling you whether person will buy insurance or not, and activation is sigmoid. I'm initializing the weights to be 1 and bias to be 0. So this goes back to the picture that we had, which was, let me just show you that picture. So it is this picture here. So 2 neurons, okay, as an input. So where is 2? So it is this 2, activation sigmoid, kernel initializer 1. So you see these weights are initialized to 1 and bias is initialized to 0. So that's why I have 0. All right, now I will do model compile. In model compile, I'm using binary cross entropy, because all you experts know that binary cross entropy is same as log loss. Excellent. And now I will do model.fit, and model.fit will run the training. It will go through all these training samples, and I'm specifying my epoch to be 5000. I figured this out by trial and error. I initially tried 1000, 2000, whatever, and then 5000 gave me the best accuracy. All right, so you can see the loss was 0.4631. So this is that same loss. This loss is this one. Once you go through all your training samples, what was the loss? 4.31. So what happened was, when we ran our first epoch, see first epoch, the loss was 0.7113. So it was this first epoch. Okay, and then we ran again a second epoch. So when we started second epoch, after adjusting my weights, my loss was this. So I kept on running this until my accuracy on my training samples came to be 90%. This is 91%. So it looks pretty good. Now you can evaluate your model on your test dataset. So my test is y test and x test scale, of course. And when you do that, this is your accuracy, see, 1.0. So for my test samples, my model performed excellent. It gave you 100% accuracy. That's what that means. And if you want to predict some of the values, so see x test scale. So you have x test scale and you are predicting the values. So let's see. This is your x test scale, and I want to predict. Okay, so what this is saying is, and you know the scale is like we divided by 100, but actually this is 47 years of age. So if it is 47 years of age, affordability 1, then the output is 0.7. So if anything is more than 0.5, it means person will buy the insurance. So let's look at our CSV file. Where is my 47? Yeah, this one. See, 47 and 1 will buy the insurance. 1, perfect. So my model predicted it right. 18 years and 1 affordability will not buy insurance because this is less than 0.5. So let's see. Yeah, see, 18 and 1 person will not buy the insurance. So again, excellent prediction. 61 and 1 affordability. So 61 and 1, the person will buy the insurance, and that's what my model is saying. 0.82 is more than 0.5, which means the person will buy insurance. So this model is performing excellent. And if you want to verify, y test. So the first one is 1. See, this 0 means anything less than 0.5. Okay. All right. Now let's look at So now I want to know, by the way, what was my final weight. I want to know my weight 1 and weight 2 and bias. Like again, going back to this example, I want to know what was this weight 1, weight 2 and bias after I train my neural network. For that, you can use getWeights function. So in your TensorFlow Keras model, you have this method called getWeights, and once you get that, when you print it, so the first one is coefficient. So W1 was 5.0, W2 was 1.04, and your bias was minus 2.91. Okay, so this was 5.0, this guy was 5.0, 1.4, so this guy was 1.4, and bias was minus 2.91. All right, now I used TensorFlow for this. Now I want to implement the same method from scratch in Python. So now you're getting into building a neural network from scratch without using TensorFlow. Okay. All right. So before we do that, let's do some simple prediction. So you all know how you can define a sigmoid function, by the way. We have seen this again in the activation function tutorial. We wrote this Python method, so this is not new if you have seen my previous tutorial. And the sigmoid, to test it for some sample value, let's do this. Okay, so this is your sigmoid. Okay, now your prediction function. Okay, so what is a prediction function? Okay, so my prediction function takes age and affordability, and it will tell you if person will buy the insurance or not. So if you look at prediction function, it's nothing but this. So weight 1 into age, weight 2 into affordability plus bias. So let's do that first. Okay, so weight 1 is what? Okay, weight 1 is coefficient 0. Okay, so weight 1 into age plus weight 2, which is 1, into affordability plus intercept. Intercept is nothing but a bias, and this is your weighted sum. Okay, once you got weighted sum, which is y, all you do is call sigmoid on that y, and that is your final output. So I will say return sigmoid weighted sum. So this is my prediction function. Okay. Okay, now let me call this prediction function on this value 0.47 and 1. So my TensorFlow model gave me 0.705. Let's see if my raw method will give you the same thing. Excellency 0.7054, 0.7054. Got it, cool. So what I just showed you was how the prediction function works once you have weights and bias. Similarly, I can take the second value, which is 18 and 1. So where is 18 and 1? Yeah, 0.18 and 1. Okay, and I expect the answer to be 0.355. So let's see. Well, you got the answer you expected. All right, now what I'm going to do is I'm going to implement gradient descent function in Python from scratch. So I need couple of helper methods for this. So the first one I need is a log loss, and this function we have already seen in our previous video, so I'm not gonna go over it again. If you have questions on this function, if you're asking me why the hell are you directly typing this function, then I will say, friends, please watch the previous video. We already went into detail in this function, so I'm just copying pasting. I will also define another function which is a sigmoid function but for numpy. So sigmoid numpy, which is a vector type of function. So instead of taking a one value, this function takes an array. Okay, so for example, if you do 1201, it just gives you the sigmoid of the entire array. And when you're using numpy and vectors, using these vectors could be very useful in your computation. So that's why I have this function. So now I'm going to define a gradient descent function. And remember, gradient descent function helps you find out weights. So at the end of this function, what we will find out is W1, W2 and bias. Okay, so for age, affordability, y true, epoch, whatever, it will tell you the, okay, let me remove this. So here I am specifying how many epoch I want to run. I have age, affordability, y true, and these three is nothing but your CSV file. See, age, affordability, bought insurance. So you are passing the vectors. Vectors in array 1, 2, 3 as an input here. 1, 2, 3, and how many iteration or epoch you want to run. Okay, so we already saw that we want to initialize W1 and W2 to be 1 and bias to be 0. This is random. You can initialize all of them to be 1 or 0 or some random value, it doesn't matter. And I want my learning rate to be 0.01. I'll start with 0.5 and see if it learns fast. If it doesn't, or if there is another issue, you know, I can change it to 0.01 is the standard thing that people use. And the length of the samples is the length of age. You can do age or affordability. Okay, and then I am going through for I in range epochs. So I want to run the iteration as many times as my epoch, and in the every epoch I want to first find out the weighted sum. So weighted sum is nothing but W1 into age plus W2 into affordability, okay, plus bias. Now when I call this function, by the way, see, let me show you how I'm gonna call this function. So I will call this function on a numpy vector. So I am specifying, so this age is not one age value, it is an entire row array. So total, like all this number in an array I'm passing. Same thing with affordability. And the great thing about numpy is you can do vector operations. So you are doing all this operation in one shot and you are getting your weighted sum. Okay, and what is a y predicted? Well, y predicted is nothing but a sigmoid, which is a numpy sigmoid of weighted sum. See friends, until now it should be very clear. These two things are very common for any neuron. You take weighted sum and then you apply sigmoid function. So if you look at this neuron, you see this vertical line, two part. The first part is weighted sum, second part is sigmoid. So it is extremely simple. And then you calculate your loss by applying this function. So we have this log loss function which takes y true and y predicted. So we specify y true and y predicted. We find out the loss. Okay. Now, until now this was very simple. Now once we have this, we want to update our weights, okay, based on the derivative functions that we had. So what was our derivative function? So in our presentation, the derivative function was this. So derivative of loss was xi into y hat minus yi. So what we are doing is we are subtracting from, so let's do this first. So let's do y hat minus yi. So how do you do that? Y hat minus, well, y predicted minus y true, right? This is what it is. Okay, so we did that. Now what else? We want to multiply that with xi. So xi is nothing but our age. It could be age or it could be affordability. So for weight 1, this xi would be age. Okay, so we want to multiply that with age. So let's say you multiply with that age. Okay, and then you want to sum it up. Sigma is sum it up, but see, this one, if you want to sum it up, and after summing it up, you are doing average, so 1 by n. So in NumPy, the way you do that is by doing dot product. Okay, so you do a dot product between these two, and you have to do transpose of age. Okay, so np dot transpose of that, and this is the dot product, and then you take an average. So this 1 by n is nothing but this 1 by n. Okay, you get the derivative of with respect to weight 1, and same thing you do with the affordability, which is the W2 derivative. And once we have derivative, by the way, okay, we need a derivative for bias as well. So bias derivative is this. So if you look at bias derivative, y hat minus y and simple average of that, so that's the simple mean of that. Now W1 and W2 is nothing but minus learning rate into the derivative. So again, going back to the equation, you see W1 minus learning rate into the derivative. All right, this is so simple until now. And same thing you do with bias. Okay, and then you want to print in every epoch, you want to print your weights, your loss, so that you know what's going on. Okay, all right, and once that is done, you want to return W1, W2 bias. Okay, so let's do 1000 epoch, just to be, you know, epoch is, friends, is trial and error, to be honest. So I'm just trying randomly 1000. Okay, what did we get? Okay, we got our loss to be 0.4200. Now when do you stop? Well, some people will stop when the loss changes at a very lower rate. So you see, we are already getting into that situation where every epoch we are not seeing much difference between the loss. So I think we have run probably more iteration than needed. So what I'm going to do is I'm going to stop when my loss is this. So I will stop when my loss is same as my TensorFlow function, so that I can compare my weights, that whatever TensorFlow the weights that TensorFlow give, can I replicate the same thing in my plain Python code. So one way of doing this is I pass a loss threshold. Okay, and I will say stop there when my loss threshold, so it's a new parameter, and I will say my loss threshold, I want to stop when that threshold is this. Okay, and you want to, of course, in your function you want to break when your loss reaches that level. I hope it makes sense so far. So you'll realize that at the end of 366 epoch, I got that loss for 0.4631. You know, 0.4631 was the one that I wanted to stop. Now let's compare that with our coef and intercept. So this coef and intercept was the one I got from TensorFlow. So now let's see, the TensorFlow coef W1 was 5.06. Okay, let me write it down. So TensorFlow W1 weight was this, W2 was this, and my bias was this. And compare it with our plain Python code, by the way. See, 5.05, 5.06, almost same. 1.45, 1.40, again almost same. Minus 2.95, minus 2.91, again very same. So this shows that we are able to replicate what TensorFlow did internally using our plain Python code. So if you're in a data science interview or machine learning interview, they might ask you to write code for gradient descent, then that will be this code. Okay, in my machine learning tutorial, whatever code we wrote was for regression. This one is for neural network or a simple logistic regression. We don't have any exercise, but I hope you enjoyed this tutorial. I know there was a lot of math and a lot of coding, but see, that is what is needed. If you want to master deep learning, you have to go through some of the complex topics, and I hope I made these topics a little bit more simpler in this video. So if you like the video, please give it a thumbs up. I'm going to share this Python notebook in a video description below, so get it. I will also share the insurance dataset and everything. Download it on your computer, run it locally on your computer or Google Colab, play with some different parameters such as loss threshold and so on, and see what you experience basically. In the next video, we are going to write a neural network from scratch, and in the next video we'll be using some of the code that we wrote in this tutorial. So you can think of this tutorial as part 1 of that second part 2 tutorial. So watch both of it. I will upload that video maybe in next few days, but watch these two, because again, gradient descent is very important when it comes to machine learning. All right, thank you, bye.